Today I told you, this statement because if the club score or coefficients, see if it's asked that for you, right? For the past 4 to 5 classes, more than that we were having club score on coefficients. So now we want to have the club score on coefficient in a line or two, in a line or two, one or two lines. Cluster coefficients are of course the coefficients of unitary transformations. I am very happy that I could get that word unitary or unitary transformation because it's the most important. When the cluster coefficient definition is there, then we will expect you to say or to write unitary transformation. Now we have to coin these words. Understand what I am saying? You have to coin these words. Unitary transformation is one line. Coefficients are there in other sides. And one more thing is that if you do connect all these, you will get a sentence. And then that sentence will give you actually what is plus or coefficients. The coefficients are the matrix elements of the coefficients or the matrix elements of a unitary transformation connecting two bases. Good. Nadevi. Wonderful girl. Now, anybody can say the sentence as I said? The coefficients are, in other words, matrix elements connecting two bases through a unitary transformation. You can say it here to that to here, right? So, cluster of coefficients are the coefficients of a unitary transformation which actually connect two bases. Now, if you are asked to give explanation for that, then you have to write about that equation. Can anyone say that straight away? K vector J1, J2, Jm is equal to summation over M1, M2. I am saying that actually. Summation over M1, M2, J1, J2, M1, M2. Yes, then please. J1, J2, Jm, and then again get vector J1, J2, M1, M2. Then you would have got a curly bracket down to up. And that is your J1, J2, M1, M2 and J1, J2, Jm. That will give you the cluster of coefficients, right? That's all. So again I suppose I need not take much of the time for this hour. Okay? Now the most important two units for the second quantum mechanics are approximation methods, right? All right. I have rotated here, right? So this is an important thing, approximation. Where do you need approximation? We used to say approximately I got the answer. That's first place I think we used to say the word approximation, right? Approximately it will be like this. Suppose one asks you to count 10 rupees notes. I give you 500, 10 rupees notes to you. I ask you to count. You have to give me power off power off automatic off and anga off off item charge charge is that I want to have a good charger, Bluetooth. What's that? Mic to speak with, so that it will be audible to all, or almost all the time I have to stand here to speak it to you. It will be very dangerous to see my face close. Right? You understand? Nice. It's okay, it's okay. Now, see, I started to give introduction to that. It says far off. Right? I have to speak loudly, okay? It's all right, no problem then. Right? I have to raise my voice. What it will do? It will amplify my voice, right? Use of that mic is to amplify. I myself act as an amplifier. That's all. It solves, right? Now we go back. Approximation. I give you one example. I ask you to count 510 rupees note. Yes. You start to count. You have to give me the answer, sir. Yes, it is 510 rupees are there. There are also chances for you to say, sir, I hope it is 498 10 rupees are there. In some other cases, the same people, the same Arnadevi may say, that's all 502 10 rupees notes are there. 502. Actually, you have to say me 500. If you give me the answer as 500, then that answer or the solution is dash solution. My dear, no. I have given you the problem already. I need not because I want to send it as a video. If I do repeat it again and again, what the people will think about me is why the Sai is saying it again and I am saying it because of you. They may not know that. I have given again. I give you the problem. The problem just now spontaneously strikes my mind. So, when I see your face, I don't want to go straight away to the approximation method and etc. Right? I give you a small example. This is a small example. Right? I give you 500 10 rupees notes. I ask you to count, to check whether it is actually 500 notes are there, 500 sheets are there, 500 papers are there or not. You count it and you say to me back. That's what it is. 498. And somebody says that 504. Now, if anyone comes, Krishna, she comes and says that, sir, it is 500, as he said, then the answer or the solution is that solution. It's a solution, it's an answer, right? 498 is also an answer, 502 is also an answer, 500 is also an answer. Answers are given by me, see, you, right? But 500 is the answer. My dear young boys, no boys, only girls. My dear girls, my dear girl students, why the word is not striking you back? It's very unfortunate, dear mom. You want to think it back, right? If it is 500, then the answer is, the solution is dash solution. You put a word in the dash, right? Exact solution. Your name please? Name please? Kartika. Great. Kartik means knowledge. Guru. Okay. Then the answer is exact. So I want to have as an exact solution. Now we go back to this scene. Is it possible to say exact solution for this problem? Say yes or no. I have given you a small problem. Now I ask you the question. Is it possible to say, sir, yes, 500 notes are there. Is it possible or not? Possible. So if you do say that answer, then that will be an exact answer. Now, we go to classical physics. This is an example for classically speaking. Classically speaking, it's almost all the time possible. Quantum mechanically speaking, almost all the time it's not possible. Classically speaking, it may not be possible for few cases. Quantum mechanically speaking, almost all the time it's not possible. Only for few cases it is possible. Now, do you want me to give the examples of possible exact solution cases for quantum mechanics? Yes. Right? The question has to rise in your mind immediately. Can you yourself give me an example in quantum mechanics for which you can have exact solutions? If you do, give yes please. You tell me one example. If you do, give me an example, the few examples. One out of the few examples, then I'll be more happy for the day. I have waited for an hour and also, right, to say these things. Can you give me one such example in quantum mechanics for which you can get exact solution? Please think it over. So many problems are there, right? So many quantum mechanical problems are there, right? And in that problem you can say one example. Say I do write one equation, not straight away all those anyhow. H Hamiltonian is equal to minus h cross square by 2m del square plus b we have to write, right? Plus b we have to write. In the place b, if I do take example of a single electron system, hydrogen atom, then you may have write in the place of B what we are supposed to write in the place B for hydrogen atom. That equation I want for B. B is equal to very simple. You have to be strong in fundamentals, rudiments. Two charges are there, Q1 and Q2, separated by a distance R. Now you tell me B. B is equal to, yes please, B is equal to 1 by 4 pi epsilon 0 Q1 R square. R or R square? Then my dear young students, you may have to go down. Then already I said I used to draw a line, It's a horizontal line. Whether you are asking me, whether you are pulling me also to go down, It's very important. It will be interesting. Logically, I will be speaking on that with the subject. How I link the subject with my straight line, I started with a straight line already. Horizontal line. There is a platform, I said. Okay, come back. V is equal to, okay. No, I will not go beyond that. You have to go back and find it, right? So this V has to be here. Now the problem is not that one. Problem is whether we can get exact solution for one electron system or not, or a electron atom or not. So it's for you to see whether it is right or as you said this is right. And this is your K. K Q1 Q2 by R is right, or K Q1 Q2 by R square is right. And also you studied like that K Q1 Q2 by R square. Also studied that. But for what it is? Coulomb's law for? My dear, again you make me to go down with you, don't make me to. So is it interesting? Is it interesting to teach in this state? Definitely, of course. But where you are not strong, I will make all you to understand up to which you are strong. So, see, we know, we have studied this, but we don't remember this. No, see, Sir is asking us to go up beyond that, right? So, I will stop with this. These are all the things which you might be knowing well, right? We don't know. Okay. This is what problem for hydrogen atom. If the problem is for helium atom, if the problem is for helium atom, then you have to write the same Hamiltonian. The problem is we should be strong to write the Hamiltonians for the systems. First case is for hydrogen atom, then second case is for helium atom. As you know well, helium atom is having 2 electrons. 2 electrons. For 2 electrons, you have to write kinetic energies and potential energies. In addition to that, then you have to go back and see it, right? If not, if you don't have it, if you are not able to see it any book, please ask me, I will give it to you. Sir, where it is, sir? I cannot see. I am not able to find these Hamiltonians for this system or that system. Yes, it is there in our books, but you have to go and search it out. Again, if you say it's very tough for us, sir, we are having 4 papers to study, sir, you have no work, sir, so please go and search for it, then I will go and search it for you and to give it to you back, right? Right. So, now, in the approximation, what's this? So, I started saying, is it there? There running? Right. Approximations 280 can be classified into 2, separated into 2, right? Coordinate verifications for time independent and time independent. Yes, please. Coordinate verification for time independent, please. Yes, please. Here. My dear students, you have to know these are all the things which we did study in the first quantum mechanics, right? H is equal to E psi, minus I H cross dou by dou t dou psi by dou t is equal to, what is the quantum mechanical way of saying E? What is the quantum mechanical way of saying the momentum operator P? How do you say quantum mechanically the momentum operator P? Classically you would say P is equal to mv. Classically. Quantum mechanically? Classically you say this P is equal to mv. Quantum mechanically? H cross A. And then for P? Then as an operator, so P started, we say classically P is equal to mv. And to say in quantum mechanical way, we set it as H cross K. Now to say it as an operator, P is equal to some. So that's the we are made. And what is this I H cross dou by dou t? I H cross dou by dou t. Here we have, So these are all very, very important things. Do you feel that these are all important or not? Yes, that's enough for me. That's a success of my teaching on the board, right? These are all very, very, very important. You should not forget it. You should not do that, right? You have to keep it in mind always. May you not see in this note, because the notes started with quantum mechanics too. But whenever one asks, then the other one has to be in the position to answer for this thing very simply. Now, again you go back, you are asking me to go down just a little bit of the horizontal line, because what I am asking you all in quantum mechanics. But this is, I'm sorry, not this. Before this I did some other things, that's very long. In BSc or in schools. Now we are here, right? Now exercise equal to E side. Now here also, in general, the approximation methods, as we have divided into two, time independent and time dependent, according to Scottish, we have written one example equations on the board. Here also you can say that bound states. Now I ask you one valuable question. I write like this: ground states. Are all ground states or bound states? Or in general, ground states or bound states? Say so. Ground states, my dear, ground states. I could give you as many examples as possible. So many examples are pouring in my mind that you give this example to this girl, you give this example to this girl. So many examples are coming out of my mind. But if I to say all the examples for even the ground state and the bound state, the word itself will give you the meaning, my dear. The word itself will give you the meaning. Words are ground and bound. Ground. Why I bent like this, I'm not dancing. Ground energy. Bound energy. Give me one example for boundary problem. infinity, deep square well, and harmonic oscillator. Yeah, all we study these things, but we don't remember, we don't know. These are all examples of these things. Oh, you should analyze it like that. If you analyze it like that, then you can study well like Madhumita. Is your name, right? Right. You have to analyze well. You understand. At least you realize it at this point. Why these are all important when to say about the approximation is all important, right? Why all these are important? To understand these approximations, we got to be strong enough in all these things. If at all you are strong enough in all these things, then it may be this and that. You can write all the notes like this, but you cannot understand not even a single line or single equation in that. I will explain you very, very important equations, but for you to see that, oh, again that get vector, first order approximation, second order, so many things are there. I will explain you. Very beautiful answers are there, but you have to be strong with these things. I am actually taking this class for all the students of our university, but whoever come across in this way to see this, all may understand, approximation method is this. They will have a clear idea about that. Are you getting clear idea now? Like you all, they will get clear idea. Picture about the approximation methods. Yes, we go back. Ground state, the mode state. Hide this slash over there, right? Ground states are mode states. Okay. Then there are version? Then down to that, sir, when you write, sir, you put one arrow like this, then another arrow has to be here like this, you know, as we have two arrows here. And there may be bound states, and here opposite is opposite to bound. I'm not able to have a voice. Excited states. Unbound states. Unbound states. Bound states, this state is unbound states. Scattered states. You can speak about that approximation. You can give a very big introduction about that approximation states for 2 hours. For 2 hours by giving examples as well in places. We need not go up to that. We have to have a basic introduction, basic idea about what is approximation method. I am actually having a confinement according to our syllabus. In your syllabus, you are having 2 types of theories under that approximation method. Time independent and time independent. So I am confining in that, right? Perturbation theory, and under this there are 2 other special cases are there. 2 other cases are there. One, another. What is one? No. Yes, good. Non degenerate case. And here it is degenerate. As I said, you know, for For each and everything, for each and everything, I have to give you examples. So now we are having two things, non-degenerate case and degenerate case. First thing we have to define what do you mean by degeneracy and what do you mean by non-degeneracy. These questions are under part B. Can anyone say degeneracy means? Can anyone ready to say it to me? Because all you are in offline. Degeneracy, as I think, sir, it will be like this, sir. May your own answer. Yes, please. Yes.
Different state of equal energy.
Good. Very good. Hemala is louder, please.
Different energy states.
You different states are having same energy, then it is degenerate. See, if it's not like that, non-degenerate. Am I right? Right? As you said, I said, I think. Right? That's what you intended to say, right? Different eigenstates having same energy level or energy value or energy. Suppose two states, two eigenstates, two eigenstates. You can say it as it please. Two states, but you have to be there in the boundary. Two states, two eigenstates, or other way to say this, two states, two eigenstates are two states, two eigenstates, eigengets, get vector are two wave functions. Right? If two wave functions are having same energy, then it is degenerate. If it's not non-degenerate. In non-degenerate, 1 to 1. One function, one energy. And another function, another energy. Another function, another energy. 1 to 1. So there are two cases. Non-degenerate case and degenerate case. Then as I said to you, we can give you examples for each and everything. So that will be a class for 2 or 2.5 hours will go if I give you examples for